This presentation is parallel topological sweep. This is an example of line arrangement. Given a line arrangement, topological sweep reports the vertices of the arrangement in a topological order. The data structures for the topological sweep are the upper and the lower horizon trees. On the left is the upper horizon tree. When two lines meet, the line coming from below has a higher precedence in the upper horizon tree. On the right is the lower horizon tree. When two lines meet, the line coming from above has a higher precedence. When we take the set intersection of the upper and the lower horizon trees, we get L1 is stopped at L2, L2 is stopped at L1, L3 is stopped at L4, L4 is stopped at L5, and L5 is stopped at L4. The figure on the left is the set intersection of the horizon trees. L1 and L2 form a ready pair. L4 and L5 form another ready pair. The sweep line may cross the ready pairs. When the sweep line crosses L4 and L5, L5 needs to find its next intersection point in the bay beyond L4. The bay beyond L4 consists of L3 and L1. L5 needs to traverse this bay to find its intersection point. This example has three ready pairs. In order to process the three ready pairs in parallel, we make this observation. When L7 crosses L6, it needs to traverse bay 3. L7 will not intersect L5 in bay 3. Similarly, when L5 crosses L4, it needs to traverse bay 2. It will not intercept L2. So all the processors may read the horizon tree simultaneously and find the intersection point for the ready pairs. The important part is after they find their new intersection points, they must hold off updating the horizon tree until all the processors have finished reading the horizon trees. Then they can start to update the tree. So we may process the ready pairs in parallel. The next question is, how many ready pairs are available for parallel processing? We need to use a line point duality to establish a probabilistic argument. In the duality, a line becomes a point and a point becomes a line. In part A of the figure, two lines in the primal space intersect at a point. In part B of the figure, in the dual space, the intersection point becomes a line, and this line crosses the two dual points. In part C of the figure, we perform topological sweep of the arrangement. We walk the underside of the top line as if we are in the upper horizon tree. We walk the upper side of the lower line as in the lower horizon tree. And the upper side and the lower side meet. In the dual space, the underside becomes a clock hand starting from 12 o'clock, and it rotates until it points at the other line. And the upper side of the lower line becomes a hand, like a clock. It points at 6 o'clock at the beginning, and then it rotates until it points at the other line. When the upper side and the lower side become the two hands, and the two hands line up in the dual space, they become the dual of the intersection point. This is back to our example of line arrangement. On the left is the set intersection of the upper and the lower horizon trees. On the right is the dual arrangement. L1 and L2 form a ready pair. In the dual arrangement, the upper hand of L1 points at L2, and the lower hand of L2 points at L1. Similarly, L4 and L5 form another ready pair, and their upper and lower hands point at each other. L3 is alone. Its upper hand points at L5, its lower hand points at L1. We are ready to calculate the expected concurrency at the beginning of topological sweep. We generate the arrangement by the dual points. The dual points are uniformly distributed in the unit circle. We sort the points by their x-coordinates. The n x-coordinates divide the unit circle into n+1 vertical strips. And at least the ceiling of n divided by 2 vertical strips have width less than 4 divided by n. Otherwise, the strips will be wider than the unit circle. We want to, when 2 points pi and pi plus 1 form a ready pair, then the upper hand of pi must point at pi plus 1, and the lower hand of pi plus 1 must point at pi. It means the shaded pi above pi plus 1 and the shaded pi below point pi must be devoid of other points. The area of if we make sure pi plus 1 is in the top quarter of the line and pi is in the lower quarter of its line, then the area of the pi above pi plus 1 is less than the triangle with a height of 1/2 and a width of 4 over n. Similarly, the pi below pi has an area less than the triangle. So the pair is ready with this probability 1 divided by 16 and 1 minus 2 over pi n to the power of n minus 2. And since there are many strips, at least n divided by 2 strips with widths less than 4 over n, the expected number of ready pairs is linear. 3 implementations of topological sweep are compared. The first is the Raveling code from 2002. I implemented a new serial code and a new parallel code. The Raveling code can process 100,000 points in a little over 11 minutes. The new serial code can process 200,000 points in 12 minutes. The parallel code can process 400,000 points in about 11 minutes. The new serial code is 3.92 times the speed of the Raveling code. The new parallel code is 4.2 times the speed of the new serial code. The new implementations are available on GitHub.